Welcome to Study Loop.
For our question, we're asked to draw a diagram of the situation in which this traveler finds herself. So she follows a passage 180 meters straight west, or west would be the negative x-axis. So that's vector A, okay? And it's straight west, so it's just along the x-axis. Then it says that she travels 210 meters in the direction 45 degrees south, 45 degrees east of south. And so she travels the vector B next at an angle theta sub B, which is equal to 45 degrees, right? And then we're told that she travels 230 meters, 280 meters, which is vector C, at an angle that is 30 degrees east of north. So theta C there would be 30 degrees. And we're asked to find the magnitude and the direction of her final displacement relative to her initial value, which would be the green line, which I call vector D there. Okay, so in order to do this, we're going to break D into its x and y components, and then we are going to use those to solve for both the magnitude of D and the direction of D. Let's get a new page to do this. So first, let's consider D of x. Well, D of x is just going to be made up of all the x components of the other vectors that were used to make it. So it's going to be B of x plus C of x, because those both act in the positive x direction, minus A of x, which acts in the negative x direction. So if you draw right triangles out for B of x and C of x, we find that B of x is equal to the magnitude of B times the cosine of the angle 45 degrees plus C of x, which would be C, and this one is times the sine of the angle that is made with C, and that's the reason it's the sine is because it's opposite over hypotenuse for sine, and the opposite there would the opposite then is going to be C, and the hypotenuse then would be C of x. Okay, or the opposite would be the C, and the hypotenuse would be C of x. Yeah, so we can use C times sine of 30 to get C of x minus, and then A all acts in the x direction. So this is just going to be minus the magnitude of A. Plugging those values in for D of x, we find that this is equal to 108.5 meters. Now, same type of thing for D of y. D of y is going to be equal to C of y, because that acts in the positive y direction, minus B of y, because B acts in the negative y direction, and A has 0 y components, so we can ignore that. So C of y then is going to be C times the sine of the angle, 30 degrees, since x was C times the cosine of that angle, or excuse me, it's going to be C times the cosine of that angle, since x was C times the sine of that angle. So C times the cosine of 30 degrees minus B times the sine of 45 degrees. So plugging in those values, we find that D of y is equal to 94 meters. Now that we know D of y and D of x, we can use Pythagorean theorem to find the magnitude of D, since it's just going to be equal to the square root of D of x squared plus D of y squared. Plugging those values in, we find that the magnitude of D is equal to 143.5 meters. We can box that in as our magnitude. Next, we want to find direction. So the direction, we're going to call this angle theta sub D, is going to be equal to the inverse tangent of D of y over D of x. And that's because from trigonometric identities, the tangent of the angle is equal to the opposite over the adjacent. And the opposite would be D of y, the adjacent would be D of x. So then to find the angle, we just take the inverse tangent of both sides, and we find that the angle here would be equal to 41 degrees. And we can box that in as our solution to the angle of the vector D. And that 41 degrees would be south of west, by the way. So maybe we should go ahead and add that descriptor in so we know what that angle is making. So you would say 41 degrees south of west. And the reason we indicate that is because if you're just going from the x-axis, you could also say that this is equal to 221 degrees. But if we say south of west, then we know where that 41 degrees is coming in and box that in.